Hello ladies and gentlemen at home and the offices at the screens. Welcome to our first breakout session. Let me quickly introduce you to the topic. Based on this year's market study of Roland Berger, 2021 was a record year for additive manufacturing. Supported by trends such as digitalization, low market entry barriers, high expected market growth rates, media and market, recently low interest rates, and the industry proximity to potent investors, we experienced a real boom despite the difficult conditions. As we saw impressively yesterday at the startup pitches, the speed of technological development is still very high, and the complexity of the market is constantly increasing. So, in my opinion, it's quite difficult to assess what future markets are, which technologies will prevail and have the greatest volume, and what are the companies that determine the market. In our breakout sessions, we will hear three exciting speakers who will give us insight into their current project and their assessment of where the journey could go. After each session, we will have the opportunity to ask questions, so please use our platform to tune in. And let's come directly to our first speaker of this breakout session. He has experienced various hype phases in additive manufacturing and founded Element22 in 2011. Today, the company offers a wide variety of technologies for a wide range of industries. I'm excited to hear what Matthias Scharvogel, CEO and founder of Element22, has brought to us. Matthias, the stage is yours. Here you go.
Thank you. My name is Matthias Scharvogel, founder and CEO of Element22. I will introduce the company and give you a quick update where we are on 3D printing, what technologies we apply, and why this is also a very important and integral part of what we do. So I'll give you a quick history, where we come from, what we do, why titanium, and where we're going. So Element22 was founded in 2011, which is 11 years ago. So at the beginning years, as you can see, we focused on developing processes, equipment, and we had to do this in order to really industrialize the process. So we built a whole new system for debinding and sintering in order to scale to production. Then we started developing standards, qualifications with large OEMs, medical companies, consumer product companies. Got the first FDA approval in 2012. I'm still today in the ASTM committee writing standards. Afterward, we expanded our manufacturing capacity and wanted to ramp up to production in 2020. That was delayed due to COVID, but we're now in the process of ramping up. And I'll give you a highlight on what quantities we're about to make. So here you see how our plant looks like. On the right, you see the molding area. On the left, you see where we debind and sinter. Some highlights. So we're about 50 people. We'll be shipping about 2.5 million parts next year, components, and we will process about 15 tons of titanium powder. And as you can see, our capacity is over 50 tons of finished product. That's what we have at the moment, and we are about to double the production space next year. So what do we do? Our main core business, you see on the top left, is we manufacture components for our customers. We make them per MIM, 3D printing, but we also manufacture filters, membranes, we do porous coatings, porous structures. We manufacture tapes, porous tapes with different porosity, sheets, foils. We extrude profiles, and we also do more and more diffusion bonding, where we bond metal to metal and metal to ceramics for different applications. So how does the process look like? There's always 4 production steps for us. First step, we manufacture feedstock, which is a mixture of binder and powder. Then we shape it, and we do band and sintering. And the shaping processes we apply is molding, 3D printing, extrusion profile, profile extrusion, and continuous casting. So for us, 3D printing is a shaping process. That's all it is for us, okay? It's a process we use to manufacture products according to our customer expectations. You see why titanium. Titanium is the 9th most common material on Earth's crust. It has outstanding material properties when you do it right. Excellent strength and density, corrosion resistance. But the perception that it's so expensive comes from the fact that it's not laid out for traditional manufacturing methods. So it's really a process you want to do net shape. And that's what we do. Top left, you see the price, the powder price, how it developed over the years, and how much powder is being manufactured. What's really exciting, the next generation powder manufacturing is coming on the market, and there we actually have first couple tons in-house, and it's super exciting because it starts from scratch. So it's not sponge and then melted and then powder at the end. No, we're starting right from scratch. We make powder and then we manufacture product. So there will never be molten finished product. So what's net shape? Most of you know. So we shape the part according to what we want. Okay, so we have no material loss. In medical and aerospace, normally buy to fly is 12:1. For us, we just shape the product without any material loss, and therefore it's extremely sustainable and a clean technology. So what do we do? Medical parts, we make implants, we make external components, lots of energy parts. Oh, okay. Lots of parts for the green hydrogen, where we make parts for electrolyzers. It's a super fast-growing industry. It's a big part of what we do. We will print parts for thousands of bicycles next year, actually really thousands, over about 50 manufacturers. We make lots of luxury goods, from 3D printed heels to metal injection molded watch housings, and we have millions of parts in airplanes flying every day. So if you look at our processes, they're really complex when we get an inquiry. So we are not a company that do prototyping. We want to do high volume manufacturing. So prototypes is not what we do. We do it in seldom cases for some customers, but not really what we want to do. Therefore, here's an overview of the different 3D printing processes we looked at. You see that everybody knows on the left, powder bed fusion. And on the right, you see sinter-based 3D printing technologies and MIM. So you see, it's a very complex chart. I'm not going to talk about it. We analyzed all the different technologies, picked some to start with, where we looked at how explosive would it be with the titanium, the accuracy we can do, the surface finish we can get, and all that, and especially technology readiness level. So here you get an overview of the material properties we can achieve. You see on the left is the ASTM 1472, and on right next to it you see what we can get with MIM, and you can see we surpass it quite nice. Please don't forget, this is without hipping. We don't hip in-house. We don't need to hip because we have sintered product with a density of 99.8%, 99.9% after sintering. On the right you see powder bed fusion, and you see in the middle the material properties we achieve with our 3D printing processes. And you can see they all meet the ASTM standard, and they're comparable to powder bed fusion. This also determines, is a big part of why and how we pick the technologies that we have in-house, like, for example, lithography printing is a really great process, but the binder system required to shape the parts don't result in the material properties we need for titanium. So important. We always want to work with very fine titanium particles in order to have good surface finish and good material structure, material properties, and very low porosity. So what do we have in-house at the moment? We do cold metal fusion, lots of cold metal fusion actually. But we also have extrusion process in-house, which is an FDM and FPF printer. One is working with a filament, the other one uses pellets. And we are about ready to decide what binder jet system we will bring into house as well. And that's all I have. Thank you very much.
Thank you, Matthias. Impressive presentation. Let me directly ask, what kind of bike is that? Can you tell us about that?
It's my bike.
It's your personal one?
Yeah, it's my personal bike. That Tom Sturdy built it, yeah.
Okay.
Tom was one of our first customers.
But it's not the one that just won the world record in distance driving in an hour.
No. This is a titanium bike, and give you an idea really why it's so awesome. We are setting up with our processes that we are having that we'll be able to build a bike frame, custom bike frame in titanium for the same price as a carbon frame from Asia.
Incredible.
That's where it's going, yeah.
So audience, you are invited to ask question. I have the platform in front of me. Whatever question you have, please place it. I have one in between. You mentioned several industries like luxury industries, aerospace, etc. What will be the focus industry for Element 22 in the upcoming years? What do you think?
4 industries. Green hydrogen, medical, luxury, aerospace.
And where do you see, when we are talking about the future, where do you see the general development of the AM market? I mean, we had 2 hype phases like in 2014 and now last year, especially considering the current difficulties, where you see the next years for the whole industry.
I think there is a tremendous opportunity. I personally believe there is a lot of applications there. You just have to get automated processes and manufacture in a pricing structure that apply to the industry. Yeah, the applications are there. You just need to find the right technology. So you're priced in an area where they buy. So it is possible.
That leads exactly to the question I have in front of me from the audience. Which AM technology do you use for serial applications?
At the moment, it is, if you say AM and it's 3D printing, because we always look at MIM as additive, but classical 3D printing, the high volume is really cold metal fusion. But there's other 3D printing technologies that will follow. Okay, for me, it is not. Cold metal fusion is great. Binder jetting is good too. It's not quite ready yet for me to industrialize, but I think we will apply 4 or 5 different technologies over the next 5 years.
There's another one. Can you share more on your expectation and challenges for metal binder jetting large-scale adoption?
Excuse me?
For metal binder jetting large-scale adoption, so reach more scale.
Metal binder jetting is a great process, especially for steel. You have to keep in mind one of the great advantages of metal binder jetting is to use fine powder. When you use fine powder in titanium, it's explosive. So you need really inert systems and complex inert handling system. Therefore, there's a challenge in binder jetting titanium with fine powder. If you want to use coarse powder, it's possible, but then you lose a lot of the advantages. So it's one of the things that are still to be developed before it really comes on the market. Binder jet of titanium with fine powder.
Thank you, great. What is the motivation of using diffusion bonding for joining metals and ceramics?
That's a very good question. We diffusion bond parts together that were made by MIM, 3D printing, and sometimes traditional mething. We diffusion bond parts together. We have one part at the bottom is tape casted. We have one part in the middle was made with traditional method and 3D printed on top. And at the end, we bond them all together, and it's one part.
Very good. Thank you for the answers, Matthias. It was a pleasure to have you here. Thank you for joining us for the great presentation, answering our questions. Big applause, at least here from the audience.
Thank you.
I think you hear it virtually from the others. Thank you, Matthias. Great to have you here. So, coming to our next company, to our next speaker, they do not only combine 3D printing and related services, but are also actively involved in the development of additive manufacturing through research and training. With a very large network, I was quite impressed. They have their finger on the pulse when it comes to the topic of trends and development. I'm curious to hear what they have to share with us about their current activities. So join me all together in welcoming Manja Franke, Chief Strategy Officer at AMEXCI. Manja, stage is yours. Good to have you here.
Yeah, thank you for the introduction. I'm going to talk today about the project InShape, meaning for innovation through laser beam shaping and metal-based AM. And I first will start on introducing AMEXCI, since I guess that not everyone has so far heard about us. So we are a company based in Sweden, in Karlskoga, and were founded like 5 years ago. Since last year, we also have a subsidiary in Finland, in Tampere. And our shareholding group consists of like 12 shareholders out of Sweden. And they are in various industries like telecommunication, it's consumer goods, it's defense, automotive, and many more. So they are basically our shareholders, but also our main customers, where we want to bring AM further to them. And this is also the reason why we have joined this project InShape together with many other partners in Europe. So the project leader for the is the Technical University of Munich, but then we also have EOS in it and Oerlikon and many more that are also here today. The project itself is a 3-year project, and it's a EU-funded project. And it started 1st of June in 2022, so this year, and we are very excited to see what will come out of it. And I explain now a little bit what the goal of the project is. So, looking at where AM is today, all the machines that are out there are basically using a laser with a standard Gaussian beam profile. And of course, it has advantages, since the high laser power and the scan speed is good to use, but it can also lead to defects and overheating, spatter, or lack of fusion, which is the downside of it. And the idea of the project is to adapt the beam profile basically on the requirements that application needs. So you can see in the overview that if you take the standard Gaussian beam profile, you can also then change it into either a ring mold or a bigger beam spot. You can also split up the laser beam. And by doing that, we hope that we can reduce the production costs, and we also create less waste, and therefore less energy consumption is needed. We have a really higher production rate, and we also can maybe print more challenging materials that are currently not possible. So how this looks like, I will show 2 videos which basically show the current used Gaussian beam profile and how it could look like with using this adapted beam profile. So basically, what we can see here is that during the melting process, there is created a lot of spatter, and this is flying around, which we want to avoid. And first initial trials have shown that this is basically how it could look like with adapting the beam profile. It was much more smooth, it creates less spatter, and we can also adapt it according to the application needs. So the idea of the project itself is to work with 2 pillars. So one is the AI-based beam shaping, where EOS is the company that will provide the technology, and we will try and work on like a recipe book for tailored beam shapes that also then is like a learning process over time, and it will like develop itself. And also then we want to use multispectral inline monitoring and control to really have a machine learning based monitoring control for analyzing like the results of the process itself. And so why are we in this? We are very driven by our shareholders, and of course price is always like one of the topics, and productivity. So we have chosen one application from one of our shareholders that is a cylinder head. And looking at what is today possible is basically that we have a lot of supports. We can only place it, like 4 of them in. Now we have done the calculation on an EOS machine. But we hope that with this technology, we can basically stack them. We can achieve a higher productivity and therefore less waste. And also, in the end, we want to be competitive to die casting, which is the current manufacturing technology. Another advantage is that this would be like a faster adaptation for customer needs, and also it's lower logistical efforts since no tooling is required. So that's a very brief overview of the project itself and what we will work on for the next 3 years. So thank you very much for your attention.
What a professional timekeeping that was, Manja. Thank you so much. Awesome. Thank you. The first question I have, because when I looked at your webpage and you just presented it, it's incredible what amount of partners you have just by your shareholders. How much does that help in developing all the new technologies?
Yeah, I think it's a high driver for us in the end. I mean, it's like they have the need and they challenge us to help them succeed. So, yeah.
And a more technical question from someone who has no clue. Okay, when I've seen the 2 videos you just presented and you changed the beam profile, it occurred to me that the second one seemed to be slower. Is that the price you have to pay, or is the speed the same?
I think we are like it's the start of the project, so it's just showcases like how different the melt pool will behave. I think speed is one of the things that will be worked on for the next couple of years.
So, but the impression was correct. It was quietly slower, wasn't it? Okay, good to know that. So, questions from the audience. This is your chance to use our platform in order to ask Manja some questions. But for you as well here in the audience, we have a microphone here with us. So, whatever question you have, feel free to ask that. Otherwise, I will ask the next question. So, you are actually living in Sweden, or you are living here? So, in Sweden. So, what about the Swedish market? Because we wanted to look a little bit into the region. So you have very famous, I would say, very well-known Swedish stakeholders there. What is the approach to AM in Sweden?
I think it's getting more and more. I mean, comparison, also being German, like having worked at EOS and like being very involved in the last couple of years in the German market, I think maybe the Swedish market has still somewhere to go. But it's definitely growing, and I think more and more companies are using AM and like are developing into that field. So,
and getting away from Sweden, where do you see not only for AMEXCI but for the whole market, so the future trends in the next coming 2, 3, 4 years, especially considering the current conditions we have?
It's hard to say, but I think it's still going to grow. So we'll still develop further. And I mean, the demand is there for like new technologies, like maybe adapting it in a way, like not only sticking to what has been developed already like 20 years ago. So
you're still positive.
Yeah.
Very good. Are there any questions here from the audience? If not, Manja, thank you so much. It was a pleasure to have a great presentation. Good luck with AMEXCI in the future, and see you soon.
Yeah.
Thank you. Bye-bye. Our next speaker holds the professorship for materials engineering in additive manufacturing at our hosting partner, the Technical University of Munich. And he researches the complex interaction of materials, processes, and component properties in the production and processing of metallic structures, especially in additive manufacturing. With his projects, and this is why he's a fantastic speaker for this event, he lays a foundation for future trends in innovations. I am very curious, and I hope you are too, to see what is currently on his agenda. Please enjoy the presentation. Welcome with me on stage, Professor Dr. Peter Meyer. Peter, stage is yours. Good to have you.
Thank you. Yeah, thank you very much for the kind introduction. Yeah, obviously it's quite difficult to compete with the coffee break here in the room, but I'm hoping that a lot of people are also watching at home. So it's my great pleasure to introduce one of our projects, upcoming projects. So I put a spotlight on one specific project, and as you can see from my first slide, it's about space. Did you know that in the last year, 146 rocket launches were conducted? So in the year of a pandemic, that's an extraordinary high number. SpaceX and China are the drivers in this area. Today, or this year, approximately the similar amount will be reached, but the predictions go into the exponential range. So who is building all these rockets that are needed to bring people and satellites up into space? There are some very interesting approaches already. As you can see here, the company Launcher produced this rocket engineering made out of copper. So the combustion chamber and the nozzle, all produced by additive manufacturing, copper in laser powder bed fusion. Very innovative. Or here, the second part coming from Beam, an Additive company. And here you can see the sophisticated design with strengthening elements. And there are inside cooling channels that give the highest power to this nozzle. And that's where we start with our project. The project has the very nice title, Disco 2030, because we want to rock the world until 2030 by combining dissimilar materials into functional, large-scale and lightweight components and structures. Nico Hempel at my institute, he's the project coordinator, and now I will guide you through what we are doing. So the motivation is with multi-material design, you can achieve a lot. The right material on the right spot. So for example, if you have a hot spot and you place a highly conductive material there, you can eliminate the heat. Or you can give a high strength to a special part that is stressed most. So properties follow functions. And obviously at an AM conference, you know that additive manufacturing also has a lot of advantages. We can do near net shape manufacturing or net shape manufacturing. The freedom of design is a wonderful tool for us engineers. The integration of function into parts helps in service. So the form follows function. And our idea was, why not combine both and do multi-material additive manufacturing of large-scale components? So in our project, form and properties follow function. So what are the main objectives in our projects? We have to develop hybrid manufacturing processes that are not available yet for dissimilar metal structures. We have to develop the same for dissimilar metal and polymer structures. These are really challenging tasks. We have to define design rules, testing and simulation procedures that qualify the process strategies. The project I'm talking about is a high TRL level project. So at the end of the project, we will produce demonstrators for industrial use cases. And also, as this was a special call by the European Commission for resilience, so to develop resilient companies, sustainability and circularity plays a big role. It's not so easy if you have multi-material parts to guarantee circularity. How do you then disassemble the things? So that's a big challenge. By the way, the project proposal was very successful because it was a very competitive call. 45 proposals were submitted. Out of these 45, only 4 are funded. And we succeeded with the highest ranking possible. So we are very proud inside the consortium. So what are the methodologies we use? So we use processes like laser powder bed fusion to produce metallic parts. So if we look here, hybrid manufacturing of dissimilar metal structures, powder bed fusion technologies, but also DAD processes using powder. Therefore, we can guarantee to produce graded structures, so multi-material parts. The demonstrator for this section is the rocket engine. But we also produce parts, both laser powder bed fusion of one material and laser powder bed fusion second material. And then we merge it with innovative joining strategies. There the demonstrator is this large combustion engine here, where the heat exchanger is a combination of copper and steel. And for the hybrid manufacturing of metal and plastic or polymer structures, we use the laser powder bed fusion for the metal part. We use wire arc additive manufacturing also for the metal part. And then we use DED for the polymer structure. Very innovative technology by one of our project partners. And the showcase here is the cryogenic hydrogen tank, where the inliner is made out of aluminum to guarantee a diffusion-tight structure and to get higher strength. It is surrounded by a fiber-reinforced composite. So this is the methodology we use, and 9 partners with 1 mission. I'd like to introduce you the partners. On the technology development side, Oerlikon Medco, surface specialist, is taking part. On the metal polymer side, it's the Austrian Institute of Technology with their light metal section. And bridging here is Oerlikon Additive Manufacturing as an additive manufacturing specialist, and TUM with 2 chairs, the chair of carbon composites, obviously for the tank structures, and my chair, materials engineering of additive manufacturing, also as a connector for both parts, but also the coordinator of the whole project action. For the use cases, we have different companies on board. Avio, Italian space company, DLR, the German aerospace center here, then Wärtsilä, a Finnish company, very interested and very productive in naval engineering, also having a strong focus on circularity. For the metal polymer, we have a very innovative startup, Cryomotive. They want to be the big player in the future of hydrogen-driven transportation. And we have the European Welding Federation, who supports us with their skills in standardization. So as expected outcome results, we want to qualify a database for the metallic and polymer materials for these dissimilar structures. We want to develop a recipe book the users can use for the process strategies. We will develop guidelines as well as qualify our samples, but then also our final components on a large-scale level. We will develop guidelines for recycling and circularity and enhance the functional depth by sensor integration. So the project start is December 1st this year. The project will go for 3 years. And for these 3 years, we will have a budget of almost 7 million euro. So I'm happy to report the next time to you what our progress is. So thank you very much for your kind attention.
Thank you so much, Peter. Quite amazing, because I remember how often we talked about the combination of materials, and especially in large formats, very impressive. There is one question from the audience that we are allowed to ask, so let me ask the first one. Do you encounter or foresee issues and challenges at the interface of the various materials during operations for your multi-material objects? That would be one of my questions too. How do you go about these challenges?
Yeah. So definitely, and that's one of the main challenges, and probably that's the reason why such products are not on the market yet. Because you have inhomogeneous material, you have a transition from one material to the other with completely different properties. Imagine soft copper, hard steel. But with our technology, with the powder and plasma deposition, for example, we can achieve gradient structures, so to smoothen the transition. Or by our design methods, we can adopt the design to get the stress out of this susceptible region and put it somewhere else where it's not so critical. So this will be our approaches, but definitely that's a big challenge.
A lot to do, of course. I'm really, really looking forward to your report about the success of this project, because I think it's super important to do so. Good luck for the future. Peter, it was a pleasure to have you. A big applause. Peter Meyer, thank you so much.
Thank you very much.